The Marine Engineering course will be lectured by Engineer Paul Rogers. Engineer Rogers earned his bachelor's degree in mechanical engineering from the University of the Philippines and earned both his bachelor's and master's degree in naval architecture from the Kyushu University in Japan. He is currently an assistant professor in UP Diliman and a senior naval architect for Amadeus Marine. With 29 years of experience in the marine industry as a design engineer and consultant, Engineer Rogers has worked on various projects dealing with structural, hydrostatics, stability, and power calculations and analysis for different ranges of vessels, equipped with seasoned technical knowledge on naval architecture and marine engineering. His research interests have covered the field of turbomachinery, mechanical vibration, and composite materials. Ladies and gentlemen, let's all welcome Engineer Paul Rogers.
Yeah. Narinig na ba ako?
Yes, sir.
Yeah, okay.
Yes, sir.
So,
Okay, ma'am.
okay.
Sir, loud and clear.
Sorry about that. Good afternoon, everybody. My name is Paul Rogers. I'm from the Department of Mechanical Engineering at UP Diliman. I'll be giving a lecture on maritime aspects of downstream LNG industry. So our course description will be as follows. No? This course focuses on the maritime aspects of the downstream LNG industry, the driving forces for the use of LNG in the shipping and energy sector, the regulatory aspects of LNG shipping, operational and safety issues in storage, bunkering, and characteristics and design of LNG vessels and onboard machinery and systems. So since this will be a plenary session, I think this will be more general, more of a general discussion about the LNG downstream industry. Okay. What is LNG? LNG is a clear, colorless, odorless, non-corrosive, and non-toxic gas. It is called natural gas. It's mainly methane, which has been treated to remove sulfur, carbon dioxide, and other impurities. So here on this table on the right, we can see the composition, the usual composition of methane of LNG. So around 70 to 80% of it is methane. Chemical formula is CH4. And then we have traces of the other hydrocarbons and elements like ethane, propane, butane, carbon dioxide, and elements like oxygen, nitrogen, and the compounds like hydrogen sulfide, and of course, other gases. So as you can see, a majority of the composition of natural gas is primarily methane, so CH4. It's around 70 to 90% of the gas is methane. So normally, LNG is carried as a liquid at a temperature of negative 100. Normally it is carried at a very low temperature of negative 160 degrees centigrade at atmospheric pressure, where it is liquefied into a liquid. And when carried in this manner, no pressurization is sometimes done, and the liquid is kept at atmospheric pressure. The LNG is often transported as liquid methane, and when it is liquefied, it has a density that is 600 times more than the density of natural gas. So, in other words, the volume has been compressed 600 times smaller than if it were a gas. So, mas madaling i-transport in liquid condition. Methane properties, the boiling point at atmospheric pressure is about negative 160 degrees centigrade. So sometimes sa literature may makikita tayong boiling temperature na nasa negative 162, negative 165, but that is dependent on the mixture of the other gases within the LNG. So medyo naapektuhan yung boiling point ng LNG. Okay. What are the uses of LNG? In the US, LNG is used for heating, cooking, electricity generation, manufacturing, hydrocarbon processing, and it is also used as transportation fuel. So, for example, in the residential and commercial sectors, energy needs 76% is provided by LNG, for heating, cooking, drying, air conditioning, dehumidification, and on-site power generation. For other uses, 40% of the industrial sector's energy needs are provided for by the LNG. So for example, in the production of paper, metals, chemicals, petroleum, stone, clay, glass, clothing, and food processing. So it also has a big share, so 40%. And 80% is for power, for electricity generation, and a very little amount, 3%, is used for the transportation sector's energy needs. So these are used as fuel for buses, taxis, package delivery trucks, and other applications. So why use LNG as a fuel in vehicles and ships? The one primary reason is for emissions abatement. So LNG has lower emissions than marine fuel oil or heavy fuel oil. So as much as if you use LNG, we can reduce around 99% of sulfur emissions. There is a reduction of nitrogen oxides by around 80%. There is a reduction of particulate matter, and also there is around 20% reduction of carbon dioxide. So this is carbon dioxide is a greenhouse gas. In addition, LNG carriers, for example, could also use the boil-off gas from LNG cargo for production. So sa cargo vessels natin, when we carry LNG, of course, although insulated yung cargo tanks natin, pwede siyang mainitan from outside. So the penetration of heat into the cargo causes some boil-off. So nag-evaporate yung cargo, and that is usually vented. So kailangan i-vent yung evaporated LNG, because otherwise you will develop higher and higher pressures inside the cargo tanks. So kailangan i-vent off yun. And instead of venting them off, ang ginagawa normally ngayon is ginagamit yung boil-off gas as a fuel and fed into the engines of the vessel. Other reasons why we need to use LNG is because of some environmental regulations that mandate the use of cleaner fuels. So one of these is the MARPOL Annex 6. This was adopted in 1997, and that convention limits the main air pollutants contained in the ship's exhaust gases, which are mainly sulfur oxides, SOx, nitrous oxides, NOx, and also the convention prohibits the deliberate emission of ozone depleting substances. So Kilala natin ito. Ito yung mga CFCs na ginagamit sa refrigeration systems natin. Ano? So, yeah. So, merong Regulation 13 and Regulation 14 which are specific to ships. Regulation 13 is aimed at limiting the nitrous oxide emissions in ships. So, ship engines installed after January 1, 2000 with a power output greater than 130 kilowatts are limited yung amount ng nitrous oxide emissions nila. No? This is based on the speed of operation. No? And we have Regulation 14, which limits the sulfur oxide emissions in engines. No? So the regulation states that all fuel oils used in marine engines should have a maximum sulfur content of 0.5% by mass in non-ECA areas and a limit of 0.1% on a mass basis in ECA areas starting January 1, 2020. So yung ECA na ito, this is emission controlled areas. No? So merong mga areas na very stringent sa regulations with regards to pollution. No? So mamaya makikita natin kung ano yung definition ng ECAs. So there are several options for compliance to these regulations, particularly these two regulations. For Regulation 13, which limits the NOx emissions, ang choice ng shipbuilder dito is to choose an engine that will comply with Regulation 13 convention. And for Regulation 14, which pertains to sulfur oxide emissions, the options are the vessel or the company using the vessel should use very low sulfur fuel oil. So because of the additional fuel processing to remove the sulfur content of fuels, naturally, these very low sulfur fuel oils or VLSFO, these are more expensive than the usual fuels na ginagamit sa vessels. No? Another option is to use exhaust gas treatment equipment. No? So merong iba-ibang types ng exhaust gas treatment equipment. We have scrubbers. Some of these are used to treat sulfur oxide emissions in the exhaust gases. Yung iba naman, these are used to treat nitrous oxide emissions. And another option is to use clean fuels like LNG and hydrogen or other fuels na yung iba dine-develop pa lang. So although may regulations, there is a means to comply with these regulations. So let's take a look at Regulation 13, which is about the NOx emissions. So vessel engines are to have nitrous oxide limits as prescribed in Table 1. So this table indicates the different types of different levels of compliance. So we have Tier 1, Tier 2, and Tier 3 engines. So pag sinabing Tier 1, these are primarily engines installed and built on or before the year 2000. And with these engines, dapat ganito lang yung levels ng, ganito yung allowable levels ng nitrous oxide doon sa exhaust niya. So yung N dito, this represents the operating speed of the engine. So we have very low speed engines, we have intermediate speed engines, and we have high speed marine engines. For Tier 2, these are engines that were installed or built on or before the year 2011. Tapos yung nitrous oxide limits niya, if you can see, these are even lower than the nitrous oxide levels allowable for engines that were built earlier sa Tier 1. And finally, we have Tier 3 engines. This is for vessels that are for engines that were built on or before 2016. Yung nitrous oxide limits niya are limited to much smaller amounts, no? So mas mahigpit yung Tier 3 engine. So graphically, this is all indicated with this graph, no? So yung operating RPM is in the horizontal axis, and yung amount of nitrous oxide in grams per kilowatt hour produced is indicated on the vertical axis. So as you can see with Tier 3 engines, very low yung limits na napoproduce dapat ng engine na amount ng nitrous oxide. And this Tier 3 regulation is applicable to vessels with engines built before 2016, but for ECA areas only, for emission controlled areas. Yung emission, if the vessel is outside the emission controlled areas, then only Tier 2 regulation will apply. So mas less stringent yung regulation outside of the emission control areas. So we have MARPOL Annex 6 Regulation 14, which pertains to the sulfur limit. It states that for emission controlled areas, the fuel sulfur content should be not more than 0.5% on a mass basis. And for non-ECA areas, sulfur content limit is, baligtad to, itong ECA areas, 0.1% per mass on a mass basis, and for non-ECA areas, mas maluwag, so 0.5% on a mass basis. This was actually enforced in January 1, 2020. And of course, the Philippines, being a signatory of the MARPOL conventions, has acceded to this regulation. So kasama na tayo dun sa regulation na yan. And kung titingnan natin itong map na ito, the dark blue shaded areas are the emission controlled areas. So as you can see, this is in the Baltic Sea, in the east and west coast of the US, and also in Hawaii. And yun na nga, for these areas, stringent yung allowable sulfur content ng fuel. So 0.1%. If you go above that, hindi ka pwedeng pumasok sa ECA. But the Philippines is actually outside of the ECA. So non-ECA tayo. Our vessels, yung sulfur content niya can go up to 0.5% on a mass basis. Of course, ganun pa rin, since yung previous regulation kasi nasa 3.5 yung limit, but when the year 2020 came, binabaan na yung limit na yun to 0.5. So you can imagine yung amount of sulfur that is necessary to be taken out of the fuel is mga 3%, which is a lot. And that also means na additional manufacturing costs are necessary to achieve 0.5% sulfur content. And because of that, mas mahal din yung fuel, no? Kaysa sa ordinary na untreated na marine fuel oil. Yeah, so tapos if we look at LNG, it is ignitable in a percentage of 5 to 15% vaporized gas to air. So outside of that, they say that it is safe. No? So if you look at this diagram, we have percent methane on the horizontal axis and percent oxygen on the vertical axis. And they say that the only flammable area is this small area here. So if you go outside of that area, for example, if you are in the yellow area, there is too much methane and too little oxygen to actually support continuous combustion. And also, if you are on the green area, there is too much oxygen and too little methane for combustion to be sustained. So, ang sinasabi, 5 to 15% ratio of vaporized gas to air is the danger area. So maliit lang. But however, maraming recorded accidents with regards to LNG, no? So although it is said na relatively safe siya dahil maliit itong area na ito for which the vapor is combustible, maraming cases na na accidents na recorded na medyo catastrophic din yung iba, no? So this is another drawing indicating that if you have a flame, if the ratio of nitrogen of LNG to air is around 5 to 15%, so ignitable yung yung mixture na yan. But if you go lower than 5%, hindi na ignitable, and if you go higher than 15%, there will be too much methane and too little oxygen for combustion to be sustained. What are the principal sources of LNG in the world? So these graphs actually indicate the primary producers of liquefied natural gas in the year 2020. So we have Australia, Qatar, US, Russia, and Malaysia, and so on. The biggest producers actually are Australia and Qatar. And here we can see the portion of the liquefied gas imports by in Europe. So makikita natin for imports by Europe, countries like the US and Russia have recently increased their share of production and are exporting to Europe. So just a little bit of history. Ano yung first LNG carrier? So the first LNG carrier was called the Methane Pioneer. It was originally constructed as a Liberty ship in 1945 for the war, Second World War. And later on, after the war, it was converted into an LNG tanker. Yung dead weight ng vessel is 5,000 tons, and it was used to convey or to carry LNG from Louisiana to Conway Island in the UK. And it had cargo area or cargo volume that could accommodate 2,000 tons of LNG. And it was utilized as an LNG carrier for 8 years. And after 8 years, it was later converted to an LNG storage facility. So very long life itong vessel na ito. But it was relatively a small vessel. No? So in 1963, two sister vessels were made. These were launched in 1963 and entered in service in 1964. These are the Methane Princess and the Methane Progress. So these vessels were decommissioned and scrapped in 1997. So relatively, again, a very long life, mga 30 plus years, 30 plus 35 to 36 years in service. They were used to carry LNG from Algeria to Canvey Island, Essex, in the UK. And it ferried, there was a liquefaction plant that was built in Arzu, Algeria, which was opened in September 1964, and a gas storage terminal at Essex, UK, which was completed in 1964. So ito yung destination at saka ito yung source ng LNG during that time. The gas source was located at the Sahara Hassi Armel gas field, and a 482-kilometer long, 24-inch diameter insulated pipeline was built from the gas field to the liquefaction facility at Algeria, where the storage facility in Arzu, Algeria, had 3 double-walled above-ground storage tanks with 2.5 million gallons capacity. Tapos Canvey Island, yung storage facility had 7 above-ground storage tanks. And of course, from the LNG storage in Canvey Island, the gas was regasified and then conveyed to facilities in the London and Leeds area. So as early as mga 1960s, ginawa na itong activity na ito. So ito yung particulars ng Methane Princess. Sorry. Nakamute pala ako. Yeah. Okay, so ulitin ko na lang. The first vessel produced was the Methane Pioneer, 5,000 tons dead weight and cargo for 2,000 tons LNG. And then in 1963, 2 vessels, the Methane Princess and Methane Progress. These were built in 1963, entered service in 1964, and decommissioned in 1997. So medyo recently lang. It carried LNG from Algeria to UK. And ito yung picture ng dalawang vessels, sister vessels siya, length of 189.3, breadth of 24.9, and a cargo volume capacity of 27,400 cubic meters. And by then, that's early as 1964, no? They already used conventional fuel and boil off gas from the cargo. And so dual fuel na yung engines, and they provided 13,750 horsepower, giving the ship a speed of 17.5 knots. And there were 29 voyages per year for the vessels. They provided LNG to 275,000 people per year. The vessels had 9 independent LNG tanks constructed from 5083 grade aluminum alloys. and they were insulated with balsa wood, plywood, and glass fiber. So walang masyadong pinagbago, ano? Even today, even these days, ito pa rin yung insulation na ginagamit. And the cargo tanks, LNG cargo tanks, are still sometimes made with aluminum alloys. And dual fuel pa rin ang ginagamit ng iba, no? So merong conventional fuel, tapos merong ginagamit yung boil off gas from the cargo. So with liquefied gas carriers, we actually have two basic types of liquefied gas carriers. We have that for LPG, or liquefied petroleum gas, and LNG, which is liquefied natural gas. So ano yung LPG? LPG is mostly propane and butane and their mixtures. No? And they sometimes include ammonia, ethylene, and propylene in their in the LPG. No? And also, LPG is carried as a liquid, no? And sometimes it's carried fully refrigerated at a temperature of -48 Celsius for propane, and for butane, -5 degrees centigrade. No? But these are both at atmospheric pressure. And in some designs, the cargo is semi-refrigerated and partly pressurized. And some cargo is sometimes carried at ambient temperature, but the tanks are fully pressurized. So yun yung for LPG. And for LNG, LNG is a natural gas, which is mainly methane. This has been treated to remove carbon, sulfur, carbon dioxide, and other impurities. So nilinis na yung LNG, yung gas. No? And again, as said earlier, this is carried as a liquid at a temperature of -160 degrees centigrade at atmospheric pressure. Normally, no pressurization is made of the cargo, and the liquid is kept at atmospheric pressure. So here's a picture of an LNG ship, LPG ship. This is an LPG vessel. Sorry. Cargo is carried as liquefied gas at fully refrigerated temperature, as semi-refrigerated, or as fully pressurized. No? So tatlong iba-ibang combinations pwede.
Okay.
LPG ships carry a liquefaction plant to reliquefy vaporized LPG. No? So if you can imagine, dito sa cargo natin, yung cargo tanks natin are exposed to sunlight and heat. So nagkakaroon ng heating up yung cargo sa loob, even if the tanks are well insulated. You know? And as a result of that, nagbo-boil off or nag-evaporate yung some of the gases. And sayang naman kung itatapon yung gases. So in this case, LPG has a temperature of -40, LPG, temperature of -42 degrees centigrade, or for propane, or -5 degrees centigrade for butane. So hindi masyadong mababa yung temperature. Pwedeng i-reliquefy easily yung product or yung gases. But for LNG, the temperature is way low. No? So a lot of work is necessary to reliquefy the boil of gases. So instead of reliquefying the boil of gas or venting it to the atmosphere, pinipressurize ng konti, and yung pressurized condition na yon finifeed doon sa main engines or auxiliary engines ng vessel. So here are some common structures of tanks in LNG vessels. Tanks are well insulated to transport the liquid natural gas at cryogenic temperatures. And some of the tanks are prismatic in shape, as shown on the figure above, and some tanks are spherical in shape, as shown on this figure below. So there are several types of tanks that are used for LNG cargo. Tapos yung typical midship section ng LNG vessel looks like this. So we normally have an inner tank that carries the cargo, and the vessel is usually a double hull tanker for protection na rin ng cargo. Sometimes yung spaces between the primary hull and the secondary hull are filled with nitrogen to create an inert atmosphere in between the cargo and the outside. So worldwide, there are about 642 LNG carriers, and roughly 260 of these are LNG fueled. No? So ginagamit yung boil of gas as fuel for the engines. LNG carriers release less greenhouse gases because of their natural gas fueled propulsion systems. Okay. So here's an example of an LNG vessel with a spherical tank. Here are the components. We have the tank dome, the steel tank cover, the tank plating, which is the primary barrier. We have the pipe tower. We have insulation. This is outside the primary barrier. And we have a cylindrical skirt and a steel foundation deck. So the cylindrical skirt acts also as a support to the a structural support to the spherical tank. Okay, so other than the spherical design, as mentioned earlier, meron tayong prismatic design. Babalikan natin mamaya yung classification ng tanks for LNG vessels. Now let's take a look at the liquid LNG liquefaction process. When the natural gas is extracted from the earth, it passes through several processes. No? So it passes through a gas metering and pressure control process, where the gas, which is initially at a temperature of 40 degrees centigrade, is set to a temperature of between 16 to 29 degrees centigrade. And after that, it passes through a process where mercury and hydrogen sulfide are extracted or removed from the gas. And after that, carbon dioxide is removed and the gas is dehydrated. So moisture removal din, kasama nun. And this occurs at a temperature range of around 37 degrees to 12 degrees centigrade. And after this process, the gas is cooled. Gas chilling and removal of heavy hydrocarbons. So the heavy hydrocarbons are stored in another container and loaded to transport trucks. And the other portion is chilled using a propane refrigeration system. And after this process, hindi pa ito gas after this process. So it is liquefied in the next process. So here we have the liquefaction occurring at a temperature of negative 35, and the cooling and liquefaction brings it down, brings the temperature down to negative 162 degrees Celsius. So in this system, we use a mixed refrigeration system to liquefy the gas. And after liquefaction, it is now ready for storage in the LNG storage facility, whether it be onshore or whether it be on offshore in vessels. Sometimes offshore gas or blow-off gas is extracted and used as fuel. Sometimes the blow-off gas or boil-off gas is reliquefied and sent back to the LNG storage facility. So how does an LNG storage facility look like? This is a drawing of an onshore LNG storage facility. So we have an inner tank and then a wall insulation and an outer tank. And of course, the roof and the floor or the bottom are also insulated. So basic structure is you have two barriers, a primary barrier inside and a secondary barrier outside, and in between you have insulation to prevent heat transfer from occurring into the liquid cargo inside. Here we have a picture of a typical LNG carrier with its components. So we have the cargo tanks, and we have a cargo handling system. Ito. We have a cargo pump. We have an energy recovery system, a reliquefaction plant, and boil-off gas compressors. So, itong malalaking tanks dito sa baba, these are the cargo tanks. And these two tanks above are the fuel tanks for the main engines and auxiliary engines of the vessel. So in this case, the boil-off gas compressors compress the gases, the boil-off gases coming from the cargo tank and bring it up to a higher pressure for storage in the LNG fuel system. Itong dalawang tanks dito. If a reliquefaction plant is installed, then that could also be used to reliquefy the boil-off gas coming from the cargo tanks. Okay, so we've been looking at LNG carriers, but there are actually a few other facilities that serve similar functions as LNG carriers. And these are the FSU, FRU, FSRU. These are offshore facilities. The FSU is a floating storage unit. The floating storage unit is used for storage only of LNG. So there is no regasification done, only storage. For FRUs, these are floating regasification units. On the other hand, this is regasification only, and its purpose is not for storage. And we have an FSRU. This is a floating storage and regasification unit. Its primary purpose is to serve as a storage of LNG, offshore storage, and also it has a function of regasifying the liquid LNG. Okay, and if we look at LNG ships, the only difference is that LNG ships are self-propelled, but they are similar in functions to this one, to any of these three. So ang ano lang is self-propelled yung LNG cargo vessels. They have storage, and most of the time they do not have regasification facility on LNG ships. So tingnan natin kung ano yung mga parts and equipment of each type of vessel. For FSU, or floating storage units, we have cargo tanks, a power generator, a cargo handling system, pumps and piping and sensors, and loading and unloading arms or hoses. And of course, a crane or a derrick to handle the hoses. So this is for the floating storage unit. For the FRU, or floating regasification unit, meron tayong regasification plant in the facility. But wala tayong cargo tanks. So ang parts niya is other than the regasification tank, we have an LNG buffer tank, a forcing vaporizer. This is a part of the regasification system. BOG compressor or boil off gas compressor. Ini-increase niya yung pressure ng boil off gas coming from the tanks when the FRU is connected to a storage facility. And we have the LNG feed pump and a boiler. So the boiler again is a part of the regasification system of the FRU. And for an LNG carrier, we have the hull, the propulsion machinery, the main engines, reduction gears, shafting and propellers, and the rudder and control system. So ito lang yung ibang-iba doon sa ibang facility like FSRUs, FRUs, and FSUs. On the other hand, we have cargo tanks, a cargo handling system, pumps, pipings, sensors, and loading and unloading arms or hoses, and a crane and derrick, which is for cargo handling. And finally, if we look at floating storage and regasification units, ang wala lang dito yung hull and propulsion system. So meron siyang cargo tanks, cargo handling system, pumps, pipings, and sensors. Tapos meron siyang regasification facilities. So meron tayong regasification heater, open loop heat exchanger or a closed loop heat exchanger, and sometimes boilers to vaporize the LNG. So here's a schematic diagram of a FSU. So we have the cargo tanks. This is primarily for storage, but we do have machinery to produce electricity, and we have a pumping system. And we have the derricks or cranes and the cargo manifold. So at both sides for loading and unloading LNG to the FSU. So ito yung mga facilities of an FSU. This is a drawing of the inboard profile of an FSU. So we have the cargo tanks. We have probably the cargo handling facilities, and we have the crane, and we have the manifolds. And we have in the aft of the vessel, we have machinery space and a pumping station to handle the liquid LNG. So this is a floating regasification unit. As said earlier, a floating regasification unit has a purpose of simply regasifying LNG. So dito sa diagram na ito, nakadikit siya sa LNG carrier, and it receives LNG from the LNG carrier, and the FRU regasifies that LNG and feeds that gaseous LNG into to the customer. So yung customer could be a power plant or another facility that requires already gaseous form of LNG. So in this case, the LNG carrier also acts as a LNG storage facility. So again, here's a schematic of an LNG regasification system. The figure on the left is an LNG carrier, and the figure on the right is the floating regasification unit. So in this diagram, the seawater is used for heating up the LNG from the LNG carrier. So sufficient na kasi yung cargo coming from the LNG carrier is very cold. It's at a temperature of negative 160 degrees centigrade, and seawater typically is at a temperature of siguro mga around 14 as indicated here, but it could go up to around siguro mga 25 for tropical areas. So this is a heat exchanger that heats up the LNG, and the LNG comes out as gas form. No? It's already at 8 degrees centigrade. So i-convey na lang ito sa user, itong gaseous form. So here's another possible setup. Here we have an LNG carrier, an FSU, and an FRU. And from the FRU, the LNG goes to the client or the customer. In this case, the client is an LNG power plant. So the LNG carrier delivers LNG to the storage unit, floating storage unit. The floating storage unit delivers LNG to the regasification unit, and the regasification unit now delivers LNG in gaseous form to the power plant. So may difference pag ganito yung system, because sometimes the facility, for example, the owners of the power plant could just charter these vessels. No? So it could be a chartering agreement instead of having to build your own shore facility for storage and for regasification. Yung cost ng business mo will instead cover chartering costs of the FRU and FSU. Here we have a floating storage and regasification unit. As I said earlier, building an onshore regasification terminal is a large and a long-term investment and requires certainty of continuous supply of LNG. An FSRU, on the other hand, can be time chartered, shifting the capital expense to operational expense. Also, the conversion of old LNG carriers to FSRUs would allow for shorter lead times. However, ang limitations ng FSRUs is that they have a potentially smaller capacity than onshore facilities, and also a shorter lifespan because the vessel itself is subject to marine conditions. So medyo corrosive yung environment, and the action of waves and other environmental influences could shorten the life of the vessel. But again, it's a good option for the facility that uses LNG, because instead of building their own onshore storage and regasification facility, pwede na lang mag-charter ng vessel na ganito. No? And chartering would shorten the lead time and also shift the financial burden of a huge investment on a facility and put it on charter expenses na lang. These are the components of an FSRU. We have the cargo tank, and here we have the regasification units. No? So dito meron tayong closed loop unit. The closed loop unit uses glycol or ethylene glycol, which is heated by seawater. So the ethylene glycol is in a closed loop, and syempre pagdaan niya sa regasification unit, its heat goes to the LNG and gasifies it. And in turn, yung glycol, ethylene glycol will be cooled. But the ethylene glycol will be pumped up into a heat exchanger where it will now be heated by seawater. So this is a closed loop regasification unit. On the other hand, we have an open loop regasification where steam can be used to vaporize the LNG. So sa heat exchanger na ito, you supply steam, boil off the LNG, and discard the steam. Of course, instances na ganito, there is some facility to also directly extract boil off gas from the tank, feed it to a compressor, and bring it up the pressure that is necessary to deliver the gas to a boiler or a generator or to a power plant. Here's a picture of a conversion of an LNG carrier to an FSRU. So, ang idadagdag lang dito is yung regasification unit, which essentially is a heat exchanger, which in some cases makes use of seawater to heat up the LNG. So ito yung structure niya sa after regasification. Sometimes we have a fuel gas heater to help in the regasification. So again, here's another example of a converted vessel. So dinagdagan lang nung regasification unit. It transforms the LNG at -160 centigrade to gas at a higher pressure. And seawater is used to pump. Seawater is used to heat the LNG from -160 to around 8 degrees centigrade. Here's a picture of a typical offshore LNG terminal. So yung onshore facility is actually on the left side. So may arrow tayo dito indicating the shore. Sa offshore facility, nandun yung facility na gagamit ng natural gas. Here we have the FSRU. It's a floating storage and regasification unit that would be able to accept delivery of LNG from LNG carriers to the left and to the right of it. And here we have the pier structure that would serve as an mooring point or mooring terminal for the FSRU. So lalapit yung LNG carrier or yung FSU, magta-transfer dito sa FSRU, and the FSRU converts the liquid LNG to gaseous form for delivery to the clients on the shore. What are the risks associated with an FSRU? Of course, we have fire and explosion. Sinabi kanina na methane can burn only at this concentration, but marami ding accidents na actually maraming accidents pa rin ang recorded sa LNG. And another probable risk is hull breach due to collisions and grounding. So this is a huge risk because the release of LNG to the sea or to the surrounding areas could create a combustible mixture for the vicinity of the accident. And again, there are some incidents na ganun nga yung nangyari. Merong spread ng vapor which led to huge explosions. Another possible risk is the structural embrittlement due to cryogenic temperatures. This is particularly true for the steel structures ng ng vessels natin, ano, whether it be LNG carrier or FSU or FRU or FSRU, because when steel is subjected to very low temperatures, ano siya, nagiging brittle, ano? So yun kailangan ding iwasan. And sometimes ginagamitan ng water curtain yung yung ship, so that any spillage onto the vessels from the transfer hoses would not cause very low temperatures on the steel structure. Of course, personnel contact with cryogenic temperatures could also cause some accidents for the personnel. What are the design standards that are used for LNG vessels, FSUs, FRUs, and FSRUs? Isa sa mga entities or organizations na have design standards are the classification societies. Primarily active among these classification societies are those that are members of the International Association of Classification Societies, like the ABS, Lloyd's, DNV, BV, GL. And there's also a standard, the IGC code, which is used for the construction of equipment of ships carrying liquefied gases in bulk. Of course, the design constraints would be, other than the particulars of the mission of the vessel, merong constraints yung environmental regulations. And of course, these are the sulfur oxide emissions, particulate matter emissions, NOx, CO2, and solid and liquid waste regulations. And of course, design constraints din yung programs for environmental footprint reduction, like EEDI, SEEMP. EEDI is Energy Efficient Design Index, and SEEMP is the Ship Energy Efficiency Management Plan. And of course, yung emission control areas, they influence the type of engines that is used for the vessel, dahil defined yung emission limits. No? And yeah. Okay, so I think it's time for a break. We'll have a 5-minute break, and we'll get back to the lecture, and I'll start the discussion on the design of tanks. Okay.
All right. Thank you, Engineer Rogers. We will now have a 5-minute break. Please be back here by 3:15 p.m. Thank you.
Okay, thank you.
All right, it's 3:15 already. I hope everyone is here. Let's proceed to the second part of our lecture.
Yes, thank you, Anjelu. Okay, so now let's take a look at the design of gas carrier tanks. No? So there are primarily two different types of tanks. We have what we call the integral tanks, and we have the independent tanks. The basic difference of these two are is that the integral tanks actually are integrated with the hull structure. So as such, they also carry some of the structural loads that the main hull structure gets. But on the other hand, we have independent tanks. These are tanks that are self-supporting and not really a part or integral part of the hull structure, and therefore they do not carry hull girder loads and do not contribute to the hull structural strength. In independent tanks, we have three types. We have type B, type A, type B, and type C. Type A tanks carries LNG or LPG at near atmospheric conditions, atmospheric pressure, um, but at refrigerated temperatures, cryogenic temperatures. So the design pressure is low at 700 millibars. For type B tanks, these are prismatic or spherical in shape, and these are primarily used for mid-sized and large LNG carriers. As a partial secondary barrier in the lower part of the cargo hold is constructed to recover any leaks should they occur. They are similar to type A tanks in shape and maximum pressure and provide better volume optimization than their spherical counterparts. And type C tanks, these are insulated, cylindrical, bilobe or trilobe shaped tanks that can be fully or partially pressurized. Typically installed on small and mid-sized carriers. Secondary barriers are not normally required due to the capacity for storage at high pressures. But due to the shape, the cargo volume efficiency is not too high. So this is an example of a type A tank. It's prismatic in shape, and they have a secondary barrier to contain any leak for a number of days. So in this structure, we see the primary barrier, the inner side or the inner tank, and we have the secondary barrier, which is the outer hull of the tank. And on the figure on the right, we see the structure of both tanks, the inner tank and the outer tank, as well as the insulation in between. So here we see the aluminum cargo tank inside. It has reinforcement, and then we have the steel hull. And again, in between, we have insulation in the form of PVC foams or balsa panels. Normally, yung aluminum is better than steel because for the inner tank, for the inner space, because the aluminum can withstand the lower temperatures without any embrittlement of the metal. And normally, meron pang inert space in between the insulation and the inner tank to provide an additional insulation for the cargo. Type B tanks are shown here. So meron tayong main meron tayong inner tank, and we have some external insulation, and we have a protective cover for the inner tank. And the shape of the tank is spherical, and inside we have a vertical tubular support for piping and also access to the tank. And there is a drip tray below to accommodate or to gather any leaks that will form or that could form from the cargo tank. And for Type C tanks, these are designed as cryogenic pressure vessels. So pressurized yung condition ng cargo dito, hindi atmospheric pressure or something near atmospheric pressure. So pressures could range above 2,000 millibars, and the tanks are designed to be pressure vessels, using conventional pressure vessel codes. These tanks do not require a secondary barrier. Rather, to detect leakage from the tanks, the cargo hold space is filled with inert gas or dry air, and sensors are placed in the hold space, which can detect the changes in composition of the inert gas or dry air due to vapor pressure or vapor of the fuel. And leakage can therefore be detected and prevented. So dito, no, in between the cargo tanks and the hull, ito yung ginagawang inert space. Tapos nilalagyan ng sensor to be able to detect any leaks from the cargo tanks. And the cargo tanks are normally in a pressurized condition. So here's two independent tubular tanks, and here we have a bilobe tank with a longitudinal bulkhead in between. We also have membrane tanks. These are non-self-supporting structures or not independent. So ibig sabihin, integrated siya with the hull structure, and therefore it could carry some of the structural loads that the hull structure also sustains. But as you can see, we have a primary membrane inside, primary insulation, and then we have a secondary membrane, secondary insulation, and last we have a hull structure outside. So yung load carrying structure nito would be the outside structure. Sometimes yung primary membrane and secondary membrane are really for containment of the cargo and for containment of the cargo, and not for structural strength. And of course, the insulation is provided to prevent massive amounts of heat transfer to occur into the cargo. So again, if you look at the classification of the LNG tanks, we have integral tanks and independent tanks. The independent tanks are classified as Type A, Type B, and Type C, and the membrane tanks are integral tanks. So integral tanks carry some structural load, but the cargo is primarily in a refrigerated or cryogenic condition, but at atmospheric pressure. On the other hand, with the independent tanks, these tanks do not carry any structural load. They are not really connected rigidly to the hull of the vessel, and we have Type A and Type B at low pressures, but Type C is a fully pressurized design. Okay. Now let's take a look at the bunkering operation, precautions, procedures, and checklists. So bunkering is the process of transferring oil supplies to the ship, and it is normally done in ports before, but now it can be done at sea under normal weather conditions. And this is called ship-to-ship transfer or ship-to-ship bunkering. So yung bunkering, it could be bunkering from an onshore facility, or it could be done from trucks, or it could be done from ships. So in case, depending on the source, it could be a shore-to-ship bunkering, truck-to-ship bunkering, or ship-to-ship bunkering. And the receiving ship is a vessel that receives the LNG from the source. What are the advantages and disadvantages of ship-to-ship bunkering? For the advantages, we no longer need to turn the ship off course for bunkering because it can meet up with the bunkering vessel on the sea. It saves a lot of time that takes to go to a particular port for the purpose none other than bunkering. No? So instead of checking into port, docking the vessel, berthing the vessel, and waiting for truck lorries or onshore supply facility to fill the vessel with fuel, you don't have to do that. Ano? Pwede na lang sa dagat gawin yung bunkering operation. Ano? And there is no need to wait in long lines for the berth and to bunker. And another advantage is that the bunkering procedure at sea is relatively easy, quick and easy. Also, when at sea, you avoid traffic at port and reduce the waiting process. Reduced waiting process also means longer process for loading and discharging the fuel. So it's to the advantage of the vessel. And also, there is no need to pay extra charges at port for berthing. Disadvantages, number one, there is difficulty maintaining position of both the ship and the bunker barge with respect to each other. So kailangan naka-moor securely yung both vessels sa isa't isa. And the whole process at sea is not much faster in comparison with bunkering at port. There is no, ang isang malaking disadvantage is sometimes ship-to-ship bunkering is not really available in most places in the world. And also, in case of some emergency, the time for response would be much slower because the two vessels are in the sea. Of course, we can expect that when the vessels are docked in port, any accident or any incident will have a quicker emergency response than if the vessel were offshore. Also, when the vessel is at sea, there is a higher risk of collisions, and as a result of collisions, unwanted oil pollutions or unwanted spills and accidents. And this actually, there are actually recorded incidents of collisions during bunkering of LNG. And of course, different arrangements are needed for different types of ships to supply fuel at sea. So so the bunkering barge also has to be ready for supplying LNG for different types of vessels. What are the preparations and checks before doing bunkering operations? First, there has to be a ship compatibility study. The bunkering barge and the receiving vessel have to clarify each other's roles and responsibilities. They have to agree on a delivery location with the proper permits in place. And if the vessel is bunkering on port, does the vessel fit the jetty? And also, they have to check if the if the hose lengths or the piping lengths and dimensions are correct for the operation. And also, they have to check whether emergency shutdown equipment are available. There are two basic types of emergency shutdown. Number one is stopping operation, and number two is through the use of a quick disconnect or quick separate hose or loading arm. So there are designs of quick connect, disconnect hoses, whereby if the hoses is pulled, if the hoses are pulled apart, there is a closing mechanism on each part of the hose to prevent any spillage of of LNG from either side, whether from the bunkering barge or from the receiving vessel. What transfer equipment are needed? These also have to be checked. The hoses, breakaway couplings, are they intact or are they working properly? Lifting equipment for the hoses, are they available? Quick connections and disconnections, are these available? And water curtains for hull protection due to steel embrittlement at low temperatures. Are these to be made available? So these things have to be checked before bunkering. And before connecting, the vessels, grounding must be made between the two vessels to prevent any electrical spark that could occur anywhere. And also quantity and quality measurement has to be done to the satisfaction of both the bunkering side and the receiving side. And of course, the personal safety equipment should be worn properly by all personnel engaged in the bunkering process. And finally, all safety procedures are to be checked and counter-checked and agreed upon by both parties. Now let's take a look at a sample bunkering process. This is for a vessel, the Viking Energy. Here we have the vessel. This is the LNG terminal. We have an LNG onshore facility somewhere here that will deliver LNG to this vessel. So this vessel will moor or berth here, and connections made, and then bunkering will proceed. So here's the vessel. This is the mooring facility. Dito siya didikit. And here we have a schematic diagram of the onshore storage facility and the receiving ship. So this is a very much simplified diagram, just to indicate how the bunkering process would occur. Okay, so here we have on the onshore storage facility, we have the storage tank. We have piping. Some of the piping have vents, and some of the piping connect the liquid line with the vapor line. So this inner loop contains the pump. This outer loop does not contain the pump, but it has a vent. And here we have some valves that control the where the fluid or the LNG could go. And this represents the loading unloading manifold on the shore side, and this represents the loading and unloading manifold on the ship side or the receiving side. And here we have the tank that has to be filled, and we have a nitrogen battery. So the nitrogen battery is a set of tanks that contain nitrogen, and the nitrogen is used for inerting the piping. Okay, so the initial step is pre-cooling. So the pre-cooling of the filling lines should be done during the vessel berthing and mooring. So beforehand, this operation can already be started when the vessel approaches the berth. So ano yung ginagawa dito? Una, you allow vapor to go through the pipes, itong outer pipes, and vapor lang muna. Ang intention dito is to allow some initial pre-cooling of the piping, because the LNG is at a very low temperature, This is normally at ambient temperature, so there's a difference of around 130 degrees Celsius. So pag hindi pre-cooled ito, there could be some sudden flashing of liquid to vapor, and that could lead to sudden increases of pressure dito sa piping. No? So kailangan palamigin ng maigi yung piping. But this is still pre-cooling dahil ang ginagamit ay vapor muna. And then you allow liquid LNG to flow through the piping. So this is much colder, and but hindi muna ginagamit yung pump. So when the liquid fully fills the lines, then you have fully cooled or pre-cooled the piping. This occurs at a duration of around 45 minutes. But then you also need to cool the piping system where you have the pump. So what you do is you allow liquid to flow through the inner loop. Then after that, which is around 15 minutes until ready for filling, now we go to the next process of connecting the bunker hose. So ito na yung bunker hose. It connects the manifolds of both sides. But as said earlier, before the bunker hose is connected, dapat i-ground muna yung both sides. So there has to be provided an electrical connection or a grounding connection between the two sides to prevent any possible arcing to occur. So yun muna before the hoses are connected. And then after the connection of the bunker hoses, we now go to the inerting the connected system. So here you can see the vessel supplying nitrogen to this pipeline. So in other words, vinavacate yung pipeline, pinupuno ng nitrogen to remove any moisture or oxygen that exists in the pipeline. And once the liquid nitrogen has inerted the system, we now allow LNG vapor to permeate the piping. So the LNG vapor will now push the the nitrogen out of the pipe. So with that, pagkatapos nun, now we have a piping system na puno ng LNG vapor. And now we have now purged the connected system. Now we allow for the filling. So we open the pump and allow liquid LNG to be delivered from the storage tank to the tank that has to be filled. So the transfer speed range will vary depending on the size of the tanks, the size of the piping, and the type or the power of the pump. And after filling operations with liquid, we have a sequential filling operation for pressure control of the receiving tank. And the duration of LNG transfer for this vessel is approximately 2 hours. So during transfer of LNG from cargo storage, from LNG storage to the tank, the tank pressure has to be continually monitored. So after the tank has been filled, the pumping operation is stopped and the gas is allowed to generate on the pipes. No? So yung heat coming from the environment will hit the pipes and will create vapor, LNG vapor, and the LNG vapor will push back the liquid back to each of the tanks. So the natural gas pressure build up due to the temperature rise will force the LNG residuals in the pipes back to the tanks. And the closing of the ship side valves pushes the remaining LNG into the vessel tanks. So in this case, after the expansion of the LNG in the pipes, all liquid will now be removed from the piping. And after that, again, the liquid line has to be inerted using nitrogen. So bubuksan ulit yung valves from the nitrogen tanks, and the nitrogen is allowed to flow into the pipe to push the natural gas inside the pipes and vent it outside. So merong konting discharge, merong discharge ng methane into the atmosphere. And ethane has 25 times the carbon warming potential than carbon dioxide itself. So this is not a good process, but the industry is still searching for a solution to have this or to generate a zero emissions process dito. So after this is inerted, this approximately takes about 5 minutes for that vessel. So tutulak ng nitrogen lahat ng LNG vapor from the piping, lalabas dito, it's vented outside, and the valves are now closed. And when the transferred amount and quality of the LNG is transferred, the vessels may now disconnect the hose piping. So, and after that, they have to deliver they have to make a bunker delivery note or a BDN. This is a document that records the fuel transfer between both vessels, and the copies of the document are kept both by the supplier and the ship for further use and compliance with regulations. They have to keep the document for the next 3 years. And under the MARPOL Regulation 18, 4 samples have to be taken of the bunker, and 1 has to go to the supplier, 1 has to go to the ship, 1 has to go to for analysis, and the other has to be kept for MARPOL. So ito yung 4 na. 1 is to be kept on board, 1 is given to the bunkering ship, 1 is for analysis, and the other 1 is for storage for MARPOL. So looking back at the LNG bunkering sequence, we have first a pre-cooling of the onshore pipes upon approach of the incoming vessel. Then we have vessel docking and mooring. Then we earth the vessel and the piping to prevent any development or generation of a spark, electrical spark. Then we establish the hose connection, and then we inert and purge the piping system, and then we do the bunkering operation. And then after this is done, we do the inerting of the piping system again, and then we disconnect the bunkering hose. So with that, the discussion on bunkering is done. Now let's take a look at marine LNG engines. Marine LNG engines are dual fuel engines that use natural gas and bunker to convert it to mechanical energy. No? So they use the fuel of the normal fuel, and in addition to that, ginagamit na rin yung boil of gas coming from the cargo or from the fuel tank to generate mechanical energy. And because natural gas has already been treated, its sulfur removed, its hydrogen sulfide removed, it is a clean gas to burn. And the addition or the use of LNG will just improve the emissions of the vessel in general. So ginagamit yung boil of gas. So the boil of gas is normally around 0.1 to 0.25% of the ship's capacity. So kung 1,000 1,000 tons yung 0.1% nun to 0.25% nun could be lost due to boil off. Lalo na kung vinevent lang yung yung boil of gas. But the boil of gas now usually is either re-liquefied or it is used for fuel as power, fuel for powering the engines. Now, what engines are normally able to use LNG fuel? So titingnan natin mamaya. What are the positive factors to use LNG as fuel? Number one, we have low sulfur emissions, and therefore the vessel can go to sulfur emission control areas, low NOx, and this is important for upcoming nitrogen emission control areas. So this is still being developed, yung NECAs. We have lower CO2 emissions and lower particle emissions. And further, there are no regulations from the IMO on the use of LNG. LNGs are as fuels. Also, because the LNG is a clean fuel, we end up with engines that are normally cleaner than usual. And therefore, the cost of the maintenance of engines also becomes less. And as a result, the cost for engine maintenance will be smaller. What are the negative factors to use LNG as fuel? Number one, design is more expensive and needs more storage space for the storage tanks. And yes, in many instances, makikita natin na itong storage tanks, instead of putting them in the lower spaces of the engine room, linalagay ito sa ibabaw ng cargo decks. There is a higher system maintenance despite lower engine maintenance frequencies. Yung system maintenance and survey costs will be a little bit more expensive. Another disadvantage or negative factor is flash point is below 60 degrees Celsius. This is considered as a safety issue because if kahit mababa in temperature, there could be the production of combustible or ignitable vapors sa vicinity. No IMO regulations exist yet regarding the use of LNG as fuels. Only guidelines. So yung guidelines na yun, for example, is Resolution 285, MSC 285. And with regards to the IGC code, Chapter 16, this only reviews main boilers and not diesel engines. So wala pa rin sa IGC code yung use of LNG as fuels. Machinery design is a little bit more complicated than the usual diesel engines, and bunkering of LNG is not everywhere available, and will therefore have safety restrictions. So these engines that use both LNG and the traditional heavy fuel oil or marine diesel oil. These are called multi-fuel engines. So the engines work in the auto process when using natural gas due to the extra amount of air required to ensure proper combustion of natural gas and to avoid notorious knocking during combustion. When natural gas is used, these are called lean burn engines because of the high air to fuel ratios necessary to burn the fuel. But with the use of energy, the benefits for the environment become more significant. Since natural gas is mainly methane, there will be no sulfur emissions, and particulate emissions and NOx emissions are cut down. So here's a structure of the cylinder head of a diesel engine, which is a dual fuel engine. So we have the typical injection pump or injection pipe through which diesel oil is fed. But here we have in the air intake, there is the connection with the gas pipe. So gas can be fed through the intake manifold and into the engine. So although they say it's a complicated structure, in theory, hindi naman ganun ka-complicated. The fuel, the LNG, just has to be fed through the air intake side and fed into the cylinder. Here's a concept design for a dual fuel powered container ships. The main engines and the generators will both be dual fuel combustion engines. This will have a lower environmental impact and also higher efficiencies. It uses fuel gas supply system, which has a very low power consumption, compact size, and it uses a high pressure liquid pumping and vaporizing system. And it uses boil off gas from the LNG cargo tanks or LNG fuel tanks. And the system of this uses an independent tank of the IMO type B. This is prismatic in shape, so it has a high volume efficiency and a good structural integrity, and it has a partial secondary barrier for the cargo. Now, of course, the boil-off gas can be either reliquefied and returned to the tanks, or the boil-off gas can be consumed as fuel. So here are the options for propulsion options for LNG carriers. So if we want to use the boil-off gas as fuel, we can use it in a steam turbine, or in a dual fuel engine, or in a gas turbine. With the steam turbine, the drive is a mechanical drive. With a dual fuel engine, this could be an electric drive or a mechanical drive. Because if it is an electric drive, the dual fuel engine will run generators, and the generators will be the ones to supply electrical power to the propulsion system of the vessel. So kaya tinawag na electric drive. And on the other hand, pwede rin mechanical drive yung system. No? So sa mechanical drive, the dual fuel engine will be directly connected to the propulsion shafts of the vessel. And with the gas turbine, this is normally an electric drive. The gas turbine is connected to a generator, and the generator provides the electricity for propulsion and other loads of the vessel. On the other hand, if the boil of gas is not to be used as fuel, it has to be reliquefied and returned to the tanks. So the option here will be to use a diesel engine. This will be a mechanical drive, and the two-stroke engine is a viable solution for this selection. So tingnan natin yung steam turbine option. Here we have the cargo tank, we have the BOG or boil of gas. The boil of gas compressor is compressed with the compressor to bring it to a higher pressure, and it is fed to a boiler. Doon sa boiler, sinusunog yung boil of gas and it generates heat, and the heat produces steam. So the steam is now fed to a set of steam turbines. So we have a high pressure turbine and a low pressure turbine. These directly drive the propulsion machinery. And also the steam can be used to drive steam turbines that are connected to generators that will generate electricity that is necessary for the vessel. So that's the steam turbine option. We have the dual fuel diesel electric option. So dual fuel yung engines natin, ibig sabihin, it takes in traditional marine diesel oil or heavy fuel oil, but it also uses natural boil of gas or forced vaporized LNG. So this comes from the cargo. It's also fed to the engines to be used as fuel. And dito sa diesel electric option, all the engines are connected to generator sets. And the generator sets deliver electricity to the main bus, which is now connected to the different loads. So we have the propulsion loads, accommodation loads, cargo dumps, cargo pumps, and compressors. Another option is to use the two-stroke engine running on heavy fuel oil, but you have the reliquefaction plant. So this is the system. It uses heavy fuel oil. Yung boil of gas coming from the tanks is fed directly to the reliquefaction plant. But and the boil of gas is reliquefied and it is fed back to the LNG tanks. The power for the reliquefaction plant comes from the power generated dito sa generators, which are connected to the engines. So in effect, mas mababa yung overall efficiency nitong system na ito kasi gumagamit ng extra energy to reliquefy the natural gas. Here's another option. We have the dual fuel high pressure mechanically operated electronically controlled gas injection engine. So here we have a high pressure gas handling system. It pressurizes gas and feeds it to the engines. So gas injection ito, tulad nung dito kanina. Yan. The same high pressure gas handling system is used to deliver LNG to the auxiliary engines, which are connected to the generators. So here we have the high pressure system. Here we already have the low pressure system. So there has to be some throttling of the LNG to a lower pressure such that it will be at a pressure that that is acceptable for the auxiliary engines. Here we have the dual low pressure dual fuel system. So walang compressor na nakakabit after the boil of gas. So the boil of gas is directly induced into the engines, whether it be the main engines or the auxiliary engines. We have the LNG gas turbine system. This is a combination of turbine and generator. No? So here we see the BOG being fed to a duct burner, and it is burned in the boiler. Some of the expansion is used to drive the gas turbine, and the gas turbine will generate electricity. We have the Rolls-Royce design and the General Electric design. So basically, ganun lang, no? We burn the LNG and expand it in a turbine. Itong malaking ano na ito na mayroong heat exchanger, this is actually a heat recovery system. No? So the gases coming out from the turbine, as the gases expand in the turbine, they still contain some amount of heat. No? So it is used for heating, and sometimes this is used for further generation of electricity by expanding the steam in a steam turbine. Here we have a steam turbine and gas engine combination. This is our cargo tank. We have the boil of gas. The gas is heated, and either it is burned in the boiler to produce steam, and the steam drives the low pressure and high pressure turbine that will drive the propulsion system. So that's one path for LNG. And the other path is for the gas to be directly fed into the auxiliary engines as shown here. And as you can see, the auxiliary engines are dual fuel engines because they take in LNG, but they also take marine gas oil. Okay. Angelo, do we have time for, I think I have several slides pa. See, okay. I'll just go ahead with the lecture now. This is a case study of a small-scale LNG carrier bunkering ship with a dual fuel engine. This study was done in Japan in the year 2014. And the process was for the design and selection of some machinery for an LNG carrier. So just to give you a background, the members of the study included shipbuilders and the association from the shipbuilders, shipping companies, 2 shipbuilders, a tank manufacturing plant, an engine manufacturing plant, and a classification society. So it's a cooperative study. And the target of the study was to create or to develop a coastal LNG carrier that would serve the coastal areas of Japan to for the purpose of bunkering vessels that ply along those routes. So it would be an LNG bunkering ship, and the ship will be a gas fuel ship. And the study came from the observation that although there were about 50 gas-fueled vessels operating in the coast of Japan, there was only one bunkering vessel that was available. No? So that was a good opportunity to study or what type or what kind of LNG bunkering ship has to be developed. So the base plan was to develop an LNG carrier and a bunkering ship. The operational route would be between Tokyo Bay and Hokkaido, and this will be used for LNG transport and bunkering. The speed will be 13 knots. The main engine for the alternator will use natural gas, and the tank type will be an IMO Type C independent tank with a capacity of 3,500 cubic meters. And the fuel was selected. There were several options, whether to use a dual fuel engine or to use a gas fuel engine or gas fuel only. So based on different criteria, the dual fuel engine was selected for that vessel. And for the propulsion system, it would be an electric propulsion system, meaning that the propulsion system, instead of being directly coupled to the engines, the main engines will be connected to generators, which will generate electricity, and that electricity will be used to power electrical motors that will be driving the propulsion gear. So yun yung naging selection sa propulsion system. And this will be the expected performance of the hull form, the required brake horsepower for 13 knots would be 1,695 kilowatts, and the maximum continuous rating for the propulsion system would be 1995 kilowatts. And this is electrical power supply demand. We can see that the electrical power for propulsion would vary according to the operating conditions. If the operating conditions are MCR conditions, the power requirement will be very high. But at departure and arrival conditions, for example, it will be relatively low. So based on this, the alternator output was decided should be greater than 757 kilowatts. And this is a study of the LNG fuel supply system. They studied whether the natural gas would be supplied from the cargo tanks or from the fuel tanks. So different cases for if the so there were several decisions that were to be made, whether to source the fuel from the cargo tank or from the fuel tank, whether to use liquefaction, whether to use gas compression, or whether to use vaporizers. Eventually, the selection process, they were able to decide to use LNG fuel from cargo tanks to LNG fuel tank, and no reliquefaction would be necessary, and the boil off gas of the LNG cargo tank will be used as fuel for the vessel. So here's the final LNG fuel supply system for the vessel. So we have the cargo tank. It will supply fuel to the LNG fuel tank. So meron pump dito, but there will be a BOG access towards the LNG cargo tank. So that BOG will be compressed and preheated and fed to the engines as fuel. Also, part of the fuel that goes through the LNG fuel tank, this will be gasified through the LNG vaporizer and fed to the gas heaters before it is fed to the engines. So ito yung naging selection nila sa system na gagamitin for fuel delivery to the engines. So this is the arrangement of the LNG fuel supply system. Merong portion, yung liquid na pupunta sa liquid fuel, the LNG, sa LNG fuel tank. And it will be vaporized before it is fed to the gas supply unit, which delivers vaporized fuel to the engines. On the other hand, boil of gas will be used. It will be compressed to the proper pressure before being fed to the gas supply unit. So here are the requirements for this bunkering vessel. Hardware, freeboard height difference between both ships, treatment of boil of gas fuel ship, and mooring of ships. So yung relative positions ng bunkering ship dun sa gas fuel ship will have to be considered for bunkering. And with regards to the software, this pertains to the bunkering procedure, mooring risk arrangements or assessments, seafarer training and qualifications, and marine disaster prevention system. So in effect, these were the main particulars of the vessel. These are the main arrangement or the general arrangement. The main particulars of the vessel will be as follows. Gross tonnage of about 5,200 tons, an overall length of 107.8 meters, breadth of 17.2 meters, a depth of 7.8 meters, a draft of 4.6 meters, a dead weight of about 2,650 tons, a speed of 13 knots, and a cargo tank volume of 3,500 cubic meters. And this will be the machinery system. So we have LNG being supplied to the engines. The engines will be connected to generators or alternators, which will supply electricity to the propulsion motors. And these are the specs of the machinery systems. And these are the specs of the LNG fuel tank, the LNG fuel supply system, and the LNG cargo tanks and the cargo handling system. So this is a isometric view of the vessel, and this is a detail of the cargo handling area that will be used for during bunkering of the vessel. So these are the arrangements. We have the two cargo tanks. We have the LNG fuel tank. We have BOG going directly to the fuel gas supply unit. For the fuel, the fuel can come in liquid form from the cargo tanks delivered here, and then that will be regasified before being fed into the propulsion to the engines. And this is a view of the fuel supply system. And this is a arrangement of the equipment in the stern area. So on the far right, we have the cargo tanks. Here we have the fuel tank. We have the fuel handling system, the gas supply unit, dual fuel engines with the alternators. The alternators feed electricity to the motors, which will provide power to the propulsion shafts. And for the last topic of this discussion, this is just this is a discussion about the preparations necessary for LNG industry expansion in the Philippines. So number one is the readiness of policy and the regulatory framework for the LNG downstream industry. This will include the shipping regulations, shipbuilding regulations, permitting systems for businesses. Another one is the development or preparation of safety systems, LNG shore facility construction and operations, and the regulations and standards necessary for the construction of storage facilities. Also, regulations and standards for vessel construction, particularly LNG carriers, bunkering barges, FSUs, FSRUs, and FRUs, and regulations and standards on bunkering. So those will be items that our different government agencies will be working on, since the LNG industry is just a new industry to the Philippines. So with that, I'd like to end the lecture. Thank you everybody for attending the lecture. I'm now ready for some questions.
All right, thank you, Engineer Rogers, for that thorough and comprehensible discussion on marine engineering. Now we'll open the virtual floor for questions. So for the participants who want to ask questions directly, please press the raise hand icon. You can also send your questions in our chat box.
You can also, if you have any questions, you can also email me. These are my email addresses. So pwede kayo mag-email kahit alin dito.
All right. So do we have any questions from our agencies and LGUs? Go ahead po. Okay. So if there's none, thank you everyone. We will provide you with the training materials, the video recordings and training presentation slides by the end of the week, along with a short evaluation form regarding this week's training sessions. So for those who haven't filled up the attendance form, kindly do so. The link is posted in the chat box. So that concludes our 5th session. We once again thank Engineer Paul Rogers and his technical assistant, Ms. Georgia Sistine, for all the time and effort you put into devising the marine engineering course. And most importantly, we want to thank all the agencies and LGUs here today for attending. Thank you very much, everyone. See you on Friday.
Thank you. Bye-bye.
Thank you. Salamat po.
Thank you.
Thank you, ma'am.
Thank you po, ma'am and sir. Thank you. God bless.
Thank you. From Kichara Fire Station. Thank you, ma'am. Thank you, sir.
Thank you, ma'am.